My interest today is in the electrical effect as it relates to material substances. We learn in chemistry, all matter is composed of atoms, and those atoms themselves are composed of electrons and protons, the fundamentally charged particles, and also neutrons, which are particles of zero charge. When matter comes together, it forms molecules, and from those molecules forms pure substances or heterogeneous substances. There are electrical effects associated with those charges, but the natural state of all material substances is neutral. There are electric fields everywhere, and wherever there's electric field, there's electric force, and whenever electric force acts on these substances, we get observable effects. That is the nature of the universe that I seek to describe. Among all of the materials that we know of in our rather advanced science and that we use in all of our industry and engineering and technology and so forth, there's a certain classification of materials. The chemists are really good at classifying atoms in all sorts of different ways, but there are classifications of materials. And the first that I'd like to discuss is conductors. There are some substances that have a loose hold on their valence electrons. In some cases, it's because the atoms themselves are quite large and the valence electrons are very far from the nucleus, and so the bond that holds them is quite weak. In other cases, the material substance itself has a kind of crystalline structure that allows different nuclei to freely share electrons. Whatever the case, there are substances that allow electrons to freely flow through the substance. So if I place that substance in an electric field, I expect that electrons will move. Last time we discussed how positive charges move in the direction of the field, while negative charges, the electrons, move opposite the direction of the field. Remember, in terms of electrical phenomenon, I'm always going to be talking about the electrons moving because their mass is so very much smaller than the mass of protons. Than the mass of protons. Protons are 1,000 times more massive than electrons. Protons are big and fat. It's the electrons that move. Materials that are considered conductors are metals and polymers, some ceramics, and graphite. All of these materials are often used in our technology to create electrical effects. They don't allow electrons to flow around with the same ease. The conductivity of a substance is described by a quantity that we won't measure or use in any equations, but it's called the conductance. Some materials are more conductive than others. Gold and silver are very conductive metals, but they're expensive, so we only use them in specialized cases. For everyday electrical use, for example, in our homes, we use copper, which is less conductive, but still very conductive. There are some ceramic materials that if you make them cold enough are super conductive, like the ultimate level of conduction that you can have. On the flip side, there are other substances where the charged particles are tightly bound, that is, the electrons are tightly bound inside of the substance. So even when an electric field is applied to the substance, the charged particles don't move much. I'm not saying they don't move at all. They do, but they can't flow. They just sort of lean one way or lean the other way, depending on the direction of the field that's imposed on them. Materials like glass, polymers, wood, and rubber. You know, it's strange. Hey, Shidley, polymers on both lists. You had polymers on the list of conductors, and now here it is again on the list of insulators. Well, when you think about polymers, you're basically talking about plastics, materials like that. Well, they come in 1,000 different varieties. Some varieties of plastic are insulating, and some varieties of plastic are actually conducting. They're sort of mesomaterials. They're sort of a little of both. When they're conductors, they're not very conductive. When they're insulators, they're not necessarily very insulating. In fact, polymers, some other substances, borderline conductors, some substances called semiconductors that are conductive under one set of physical circumstances and become insulators under another set of circumstances. A good example of this is silicon-based semiconductors. In the United States, of course, we're very familiar with the phrase or the location Silicon Valley, which is sort of the hub of microchip design and production in the United States. Microchips take advantage of semiconduction because, like a light switch, we want to be able to manipulate the electrical effect to turn on and off in the context of ones and zeros, which is essential to digital computing. So I suppose three types or three classifications of materials: conductors, insulators, and semiconductors, particularly those that change their conductance based on whatever physical conditions they're exposed to. Atoms and the substances that compose them, or composed of them, are naturally neutral. We know that in a natural state, atoms have as many electrons as protons, and since electrons and protons have the same fundamental charge, just opposite, then the sum total of that charge is zero, neutrality. We only observe electrical effects when the balance of that neutrality is thrown off. In order to create electrical effects, you have to separate charge. In general, there are three ways of doing this. You can separate charges in material substances by friction, conduction, and induction. So I'm going to take a minute here to go through all three of these processes. Despite the fact that the first process, the process of friction to separate charge, we've already talked about and I've demonstrated during a previous lecture. And that is that I can rub substances together, and through the process of friction, I can shift the charged particles. This is called triboelectric charging, charging by friction, where the valence electrons of a substance are stripped off by the force of friction. For example, I take a glass rod and I rub it with silk, and as already was discussed, the silk strips electrons off the glass. The glass was originally neutral, and when you take electrons away, it becomes positively charged in their absence. The silk was neutral, but it carries away with it an excess of electrons and thereby becomes negatively charged. I had a plastic rod, in this case I'm referring it to amber, an homage to the first observance of this with the ancient Greeks. But I have this rod and I rub it with fur, and the opposite effect happens. Well, I don't know, opposite. It's a transfer of electrons by friction, except in this case, the fur loses electrons to the rod, in which case the rod becomes negatively charged because it was neutral, and now it has an excess of electrons, giving it an overall negative charge. The fur has lost electrons. It was previously neutral, and by virtue of losing electrons, the fur becomes positively charged, charging by friction that we're already familiar with. I can also charge an object by using conduction. Imagine that I take this amber rod here and I charge it by rubbing it with fur. As a result, the rod becomes negatively charged. I could take that negatively charged plastic rod and bring it in the vicinity of this metal ball here, which is hanging from an insulating string. The reason why it's labeled insulating nylon thread is because I don't want to allow any charges to travel along the thread. If the thread is an insulator, it means that the thread will not allow charges to flow. So there that metal ball hangs, neutral. And I bring the charged plastic rod nearby, and I allow the charged plastic rod to touch this copper rod. The other end of the copper rod touches the metal ball. Now, consider the conditions on the plastic rod. An excess of negative charges are living on that plastic rod, and they are elbow to elbow. Because they are like charges, they repel. These negative charges are near each other, but they don't want to be. That statement is what we call the preposterous fallacy, the idea that electrons or protons want to do a thing. They don't have emotions, they don't have needs, wants, or desires, but what they do have is a repulsive force. And given the opportunity, the pressure of that repulsive force of all the negative charges on the rod will push them along the copper wire and onto the metal ball. If I then remove the copper wire, I'll discover that the metal ball now has some negative charges in excess on it that were transferred from the rod. The thing is, if I do this process, charge plastic rod, connect it with a conductor, allow electrons to transfer, and then remove the apparatus, I'll take the plastic rod away and I'll take the copper wire away. Now what I have is a metal ball hanging. And it looks, smells, masses, tastes, in every way physically the same. How do you tell the difference between a charged metal ball and a neutral metal ball? How do you tell if it's positive charge or negative charge? Well, in order to do that, you have to create an electrical effect. So what you do is you bring back the negatively charged rod. When you bring a negatively charged rod near the negatively charged ball, it will repel the ball. And so you know, because it's repulsion, that the ball must have the same charge as the rod, because likes repel. And since you prepared the rod in a way that assures you that the rod is in fact negatively charged, you've taken the rod and rubbed it with fur. That's what Ben Franklin called negative charging. That resonance charging was dubbed negative. Then you know that since the metal ball is repelled, that it must also have a negative charge. If you're not convinced, you could then prepare a glass rod by rubbing it with silk. Then it would have positive charges on it, and then you bring the glass rod close to the metal ball, and the metal ball will be attracted to the glass rod. And then you become sure that this metal ball is not neutral, but is in fact gained charge through the process of conduction of that charge to the object. The third type of charging is charging by induction. Charging by induction can only be done with conducting objects. What I have here is a metal sphere, so a conductor. It allows charges to flow inside of it. And the metal sphere is mounted on a stand that is an insulator. So charges can't flow through the stand. They can't get in or out of the system by going through the stand. The stand does not allow charges to flow. The stand is an insulator. So I bring in a negatively charged rod. The sphere is neutral, but that doesn't mean the charges can't move around. In fact, because the sphere is a conductor, the charges inside of the sphere will move around. That's what they do. Well, what do I expect is going to happen? I talk about it in the context of negative charges moving. Well, here comes a negative rod. All of the charges inside the neutral ball will be repelled by the negative rod, and they'll move to the right. And so you see in my diagram, I've labeled the right half of the sphere with negative charges, because the negative charges run away, repulsion, run away to the right. The negative rod is on the left, so the negative charges are forced away to the right. On the left side of the sphere, left half of the sphere, I've put some plus marks here indicating that the left side of the sphere is positively charged. Positive charges haven't moved. What's happened is when the electrons moved away from the left side of the sphere, they left the protons behind, and the protons are positively charged. The left-hand side of the sphere is positively charged because of the absence of the electrons that were pushed away. We say here that this charge has been induced. Induction implies a thing is forced to happen by an outside influence. That's induction. So the charge has been induced. The separation of charge has been induced. Now I do a rather clever thing. I get a wire and I connect the sphere to the ground. Now, literally, I could mean the ground here, the dirt outside. But ground, we're going to encounter this term a few times in some different contexts. But ground, in a scientific sense and in a technological sense, means a place where charged particles can go. Now, the sphere is quite small. It turns out because of its size, it has a limited capacity to store charge. That's really not surprising. My refrigerator has a limited capacity to store fizzy drinks because of its size. But the ground is effectively infinite in size and can hold as much charge as you like. And when the charges get there, they're not very upset because they repel each other, but they can get very far away from each other. And so it makes no difference. It's like going to the ocean in the summertime and you don't like the temperature of the water. So you get yourself a bucket of hot water and pour it into the ocean. Does that make any difference at all? No. The ocean of the world is so large that it has a nearly infinite capacity to absorb buckets of water, or the heat of buckets of water. So when I connect the wire, all of the electrons here that are trying to flee from the negative rod on account of the force that the negative rod exerts will flee down the wire and into the ground. Off they go, into the ground. And then, yoink, I remove the wire. When I remove the wire, the electrons can't get back to the sphere. There's no path for them to return. And so what I get is a positively charged sphere. The sphere was originally neutral, but I brought the negative rod near, forced the charges to separate, drained off the negative charge, cut the pathway, and now that sphere has lost electrons. It was neutral, but now it has fewer electrons, and in their absence, it is positively charged. It has been charged by induction. It's important to note, the negative charge has not been destroyed or eliminated. It is not gone forever. The charge is in the ground. I have negative signs there indicating that the charge is in the ground, but it's a little bit wacky to do that because the charges in the ground have gone off to who knows where. Just like the heat from that bucket of water you dumped in the ocean just goes off and is gone. But those electrons still exist. It turns out that there is in our universe a law of conservation of charge. So far as we can tell in our universe, charge cannot be created or destroyed. Electric charge cannot be created or destroyed. If some process, some natural process happens that transforms the charge and the count is off, that charge must show up somewhere else. Just like the law of conservation of energy. If I have a certain number of joules and I do the accounting and some joules are missing, they must have gone somewhere. Out the window, perhaps. There's a law of conservation of charge. It might occur to you that there are conservation laws all over the place. And the chemists enjoy this conservation law in particular. When you're getting atoms together to make molecules, you got +2 over here, -2 over here. All of that has to work out to zero because the total charge has to be conserved. There's another thing that the chemistry teachers imply, that the mass of the atoms that you have on this side of a chemical reaction must be equal to the mass of the atoms that you have on the other side of the chemical reaction because of the law of conservation of mass. Just for fun, let me tell you, as a matter of fact, that there is no law of conservation of mass. I can literally take mass and destroy it. I can remove it from existence. I can have a certain number of kilograms, 2.2 kilograms maybe, and I can remove that 2.2 kilograms out of existence. So it simply does not exist anymore. Shade, that sounds wild. It sounds like a magic trick. Well, it really is. Because it turns out when you do that, a spectacular amount of energy is released. And that's what a nuclear weapon is. The boom, boom, flash, burny, burny of a nuclear weapon is the mass converted into luminous energy in the form of light in that explosion. And the mass is lost. It's gone. There is no law of conservation of mass. The reason why the chemistry teachers can say that there is a law of conservation of mass is they don't let you build nuclear weapons in chemistry class, and so it's never an issue. If the energy levels stay really low, then mass seems like a conserved quantity when it's really not. But I'm here to tell you that so far as we can tell in our universe, charge is an absolutely conserved quantity. Charge can't be created or destroyed. Only moved around by electric fields. So if I charge things, they interact with each other. I get it. If two objects have like charges, they'll attract each other. And if two objects have opposite charges, they'll repel each other. And then all of a sudden, this mystery happens. This would have been very much, by the way, one of the phenomena that would have been observed by ancient Greeks that they couldn't explain. Here's a comb, an ordinary plastic comb, and some colorful little bits of paper. And the comb is brought near the bits of paper, and I'll go ahead and reveal the comb is charged because I've run the comb through my hair. And just like rubbing the rod with fur, me being a furry mammal, more than some people, I run the comb through my hair, and now electrons are stripped off of my hair onto the comb. The comb is negatively charged. I agree, 100%. But these little bits of paper shoot up to the comb. Well, in order for that to happen, Isaac Newton tells me there must be a force. But the little pieces of paper are neutral. The little pieces of paper are neutral. They don't have a charge. And if the little pieces of paper are neutral, then what I should suspect, based on everything that I've discussed so far, is that there should be no force. How do I explain this? Well, the explanation comes from looking very, very closely at the molecular structure of the paper. All material substances are at a minimum composed of atoms, in the case of pure substances, many kinds of atoms in the case of molecules, and many different molecules in the case of heterogeneous substance. But there's a lot of charged particles organized in different ways. And sometimes, just because of molecular structure, you get a little bit more charge on this side than you get on this side. That is, within the molecules themselves, by virtue of their structure, their charges can repel in such a way that a separation of charge is naturally created. When charge is naturally separated by just the conditions of molecular construction, we call that polarized. Here's a closer look at what's happening. Here I have my comb, and as I suggest, I've run it through my hair, and you can see these negatives that are on the teeth of the comb. That's electrons. The electrons create an electric field everywhere around them that points toward the comb, doesn't it? Because I've already established that my convention is that electric field points toward negative charges. So where the paper is, there's an electric field that's created by the comb, while the molecules inside the paper are now in that electric field. They look down at their feet, and there's now an electric field. Well, one side of the molecule is positively charged, and it wants to go in the direction of the electric field. The other side of the charge is negative, and it wants to run away from the electric field, like go in opposite the direction of the electric field. And so the molecule turns to line up in such a way that you can see, it's a little bit small in the diagram because I have all of these polar molecules here, such that the positive is being attracted to the negative. That's what happens, right? Opposites attract. The positive is attracted to the negative, and the negative is repelled. And so all of these polar molecules line up. And we say that the material has become polarized. Well, as a result of the polarization, the positive side of the molecule is closer than the negative side. Now remember, in our electric field law and our electric force law, it's 1 over the square of the distance. So distance really matters. Because the positive charges are closer and the negative charges are further, the overall force is attractive. The comb is attracting the paper and repelling the paper, but the attraction is just a wee bit stronger. And so the little bits of paper are attracted because of their polarization. The paper's still neutral, and yet it's attracted. I can set it up the opposite way. It's a little bit tricky to make a comb positively charged, I'm not going to lie. But it can be done. I can make a comb positively charged. And if I bring the positively charged comb toward the paper, the reverse effect happens. A positively charged comb creates electric field that points away from itself. So in the paper, the positive charges want to go in the direction of the field, that is, away. And the negative charges will go opposite the field. Another way of looking at it is the comb is positively charged and the negative of the molecules is attracted to the rod. And so the randomly organized molecules, they line up to the field. And because the negative charge is closer than the positive, here's an interesting thing. The force is still attractive because the negative charges are attracted to the positive. It doesn't matter which way the polarization goes. Polarization effects are always attractive effects. You could do this experiment with the comb and the little bits of paper. Try it out. You'll see that it's true. There's another effect that I want to present as an example because it's a very simple example. Water is a polar molecule. Here, this little thing that looks like a koala bear head, it's not. It's what you learned about in chemistry class. It is an oxygen atom that is bound to two hydrogen atoms. But by virtue of the molecular interaction, one side of a water molecule is a little bit more negative. Here on the bottom side of this oxygen atom, it's a little bit more negative on average. And the hydrogen atoms are a little bit more positive on average. And so water molecules have in them a separation of charge. But when you pour yourself a glass of water, all of the charge in the glass of water is neutralized because there's equal amounts. And the water molecules are all arranged randomly, and so there's no polarization. But if you allow water to come out of a faucet in a stream, here, there's a beautiful picture. Here I have a laboratory faucet, and a stream of water comes out, and of course, it falls because of the force of gravity. It should go straight down. But here in the image, we see a charged rod, and I don't care whether it's positive or negative. It's the same effect either way. A charged rod is brought close to the stream of water, and the molecules in the stream of water are then in the electric field created by the rod, and they align. And a force becomes attractive, and you can see quite dramatically the stream of water is deflected from its otherwise vertical path. It doesn't matter if the rod is positive or negative, the stream of water deflects toward the rod. We see these electrical effects in our everyday lives. These electrical effects are what create the structure of matter, and these electrical effects are what we do to arrange in engineering circumstances to create our technology. Sort of an unceremonious finish to that. Is there a particular slide we want to see? Boop, boop.
Yeah, can you go back to,
Of course, you also have that on the canvas, so.